it working? Yeah.
Yeah.
About the photo.
You make the announcement?
I will make it after the.
That's also where the it could also then be
Okay. I think we are getting ready to start the morning session. So it's a great pleasure to introduce Roberto Tateo from Torino University, who will talk about TT bar-like flows and links to string theory. So please.
Okay, good morning. Can you hear me? Yeah, okay. So first of all, thank you very much to the organizer for the kind invitation. And yeah, I will try to give a brief review on some interesting new evolvement of the TT bar research. Let's do it. Okay, so first of all, on the market, there are already few very nice and yeah, fairly complete review on the subject. So there is the Monica one, 2020, where it's focusing essentially on the aspect related to ADS CFT. And the second review is also on relation between TT bar and other irrelevant perturbation with string theory. And there are these two also more recent review, which are more, they contain more, they are more related to the talk I'm going to give now. So first of all, a little bit of history. So it looks as suddenly this TT bar operator appears, or TT bar perturbation appears in 2016, but actually the history is much longer. And essentially last century, more or less 40 years ago, in that period, I mean, there was a group working on integrable model. It was the leader of the group were essentially the Zamolodchikov with other important scientists. And the idea was that at that point, people could really understand very well conformal field theory and the spatial minimal model. We knew already everything about the spectrum and the correlation function, etc., etc. So the idea, the novel idea is put forward by the Zamolodchikov brother, together with other collaborator, of course, was to start to study non-perturbative aspect of the renormalization group. Okay, so and in particular concentrating on what we call integrable model. An integrable model, they possess an exact scattering matrix. You know exactly the spectrum, and from the X matrix you can calculate many important quantities. And in particular, you can calculate finite size correction exactly using the thermodynamic Bethe-Ansatz method, so thermodynamic method, which give you the theory, they can describe the theory on a box with periodic or open boundary condition, and as you change the size of this box, you can move from the ultraviolet description, which is the conformal field theory, to the infrared description, which is related to the scattering matrix description. So it's an exact method. It gives you an exact equation. It's a nonlinear integral equation, so you can solve it exactly only in particular limit. But then it's very easy to solve numerically. You can solve it with 60, 70 digits nowadays. It's not a big problem. Okay, so the idea is the following. You start from a conformal field theory, and you think about this conformal field theory as the ultraviolet fixed point of a flow. Okay, and so you choose a relevant operator in your theory, and you perturb, you add it simply in the action, these relevant operators. Okay, and then usually, I mean, the first model they discovered essentially gave you a completely massive theory, so with trivial infrared. But then there was this paper by Zamolodchikov, Alyosha Zamolodchikov, which actually modified things a little bit. So the idea, he wanted to try to understand the flux along the critical line connecting the tricritical Ising model and the Ising model. They are the lowest, the simplest model of minimal conformal field theory. And then, so he took this, started from this standard setup of scattering matrices, Jan Baxter, etc., and he managed to do analytic continuations and take the massless limit. So essentially introduce a set of scattering matrices which would describe the scattering between massless particles, okay? But then, okay, this S matrix would put in connection right and left movers, so the scattering, so the theory, the final theory is of critical in the sense that it's not, well, it's out of the conformal fixed point, but still has massless mode, okay? So this is a much less trivial setup compared to the massive perturbation. So, so essentially, at the same time, it was discovered that some of these relevant perturbations were actually integrable. It means that you have also still an infinite number of conserved currents outside the critical point. Okay, so And then you can reach when you send, for example, the size of your cylinder, when you are using thermodynamic Bethe ansatz, you flow in the infrared, which is another non-trivial conformal field theory, another non-trivial fixed point. Okay, so there were many, many people. Well, the community was actually small, but I mean, there are relatively many people working and interested in this. Oh, it's a bit slow. Okay, so this is what I described. So the first model was the flux between the flow between the tricritical Ising model and the Ising model. Okay, so so we immediately all realized that this might have been a way of study non-renormalizable theory, because we could go close to the infrared and understand what were the attracting operator, the leading attracting operator. So we could do something, but unfortunately it was numerics, so the progress was very slow. But what is important is that in this example, the leading attracting operator was this so-called name TT bar operator, which close to the infrared is just the product of T times T bar. So this is why it's called TT bar operator. Okay, and then well, just to mention that it's surprising that we were working about and try to search non-perturbative RG flow in this two-dimensional setup. And now I think there is a little bit of revival on this, and people is proposing new flow. And there is still a big question mark related to the study of non-invertible symmetry. There is still a bigger full mark whether they are integrable or not. So we are very suspicious because essentially at that time we found only essentially. Okay. So this is just to say that the hope at the time was to go back, so to start from the infrared and try to understand some scheme to go back to flow upward to the ultraviolet. And this is actually what we managed to do using the TT bar perturbation. Because strangely enough, the TT bar perturbation, the TT bar operator, leaves the theory integrable, essentially with the same symmetry, a part of cross-conformal symmetry, and give you, so it's choosing some scheme that we don't fully understand yet, but is giving an exact result, an exact flow, okay? There are no new degree of freedom in the theory, so essentially there is a one-to-one map between the conformal field theory, the original conformal field theory, and the perturb model. Okay, so first of all, so as I said at the beginning, the TT bar operator was just T times T bar, and then as you perturb the conformal theory, you go out, and the right and left mover, they start to interact, and the theory is no longer conformal, even if the perturbation is irrelevant. So you need a definition of the TT bar operator outside the critical point, and amazingly, it was instead introduced by Sasha Zamolodchikov in 2004. So there was a huge, well, quite a wide period of time. Okay, so this also doesn't come from nothing. I mean, we are always sit on the shoulder of somebody else. Okay, so this came from previous result on form factor. So for correlation function, so they were studying form factor expansion for massive theory, for massive perturbation, and they realized, and then in that case you need the expectation value of your operators, and they realized that there was always, for TT bar, there was always this type of factorization. So essentially, as claimed in the original paper, Sasha Zamolodchikov wrote this letter, this short paper, just to put, to clarify some important point that essentially were forgotten for many years. Okay, so this is the definition of TT bar operator. This is actually, it's a quantum level, but the same feature essentially hold through also a classical level. And if you go to excited state, essentially we notice that the classical properties are essentially equal to the quantum properties. So it's, the definition is done by, it's related to the fact that if you have TTD bar and you perturb your theory, so if you are outside the critical point, then you develop singularity here. But these singularities are completely cancelled by this term, which contains the square of half of the trace of the stress energy tensor. Okay? And then there are also other terms, but they are all total derivatives. So when you put the theory in an appropriate boundary condition, okay, let's say periodic or vanishing boundary condition, this contribution do not contribute. Okay, so at the end of the story, essentially at classical level, the TT bar operator is the determinant of the stress energy tensor. Okay, that can be written in any way or is proportional anyway to the stress energy tensor. Okay, so again, so the Zamolodchikov paper is actually about expectation value of TT bar on a super renormalizable theory. Okay, so it's not about expectation value of TT bar on a TT bar perturbed theory. So there is a certain number of years, 12 years, between the original paper by Zamolodchikov and the idea that I'm going to explain here. So the TT bar perturbation. Okay, so the classical idea. Okay, we first got the quantum, okay, because we were working on exact test matrices together with other people, but it end up that we need to understand, so to have a right point of view, to understand also what's happened at classical level. So the idea is the following: you start from your preferred Lagrangian, you calculate the stress energy tensor, you take the determinant of this stress energy tensor, you add it to the Lagrangian, and you construct a new Lagrangian with a new stress energy tensor. In this way, you define a flow equation for the Lagrangian, which is completely closed and associated to this pair of definition. Okay, so again, so this was essentially written down very nicely by Smirnov and Zamolodchikov, but I think the similar idea appears in previous paper. Okay, not written exactly in this way, but okay. So as I said, you start from your preferred Lagrangian, and why not? You choose. You can start from a Lagrangian with a collection of boson and maybe an arbitrary potential, which depend only on the field in this way. And the magic result is that if you apply this scheme, you move from a standard quantum, well, a standard field theory with free boson with potential, to a Lagrangian, which is a stringy type Lagrangian. Okay, so in particular, if you set the potential to 0, this is exactly the Nambu-Goto action in the static gauge. Okay. Again, this was obtained in 2016, but actually is based on earlier result by the Dubonsi group and also some little result by us. Okay, so okay, the first attempt so people solved this equation in a perturbative way, and then you have to look at the perturbative expansion and see whether you recognize some interesting object. And I mean, that was not too difficult to do, but actually, of course, Mathematica tells us tells us that you can do better, and you write the first two equations in a compact way as a PDE, and then you can solve in general this PDE using the method of characteristics, okay? Directly. Okay, so if you use the method of characteristic, of course, you obtain the earlier result when you are dealing with free boson. But you also get other interesting result. So for example, if you start from Yamil's theory, generic in 2 dimension, which is topological or quasi-topological, then you apply this method, either perturbative or with the method of characteristics, and you get a very complicated Lagrangian, okay? And for people that know a little bit of history of nonlinear electrodynamics model, then this type of generalized hypergeometric function also appear in that case. Okay, self-dual electrodynamics model, okay? But the surprising thing that if you look instead for the Hamiltonian, you do the Legendre transformation to move from the Lagrangian to the Hamiltonian, and actually the Hamiltonian is modified in a very trivial way in this way. And actually it was also proved that the same generalized hypergeometric function and the same sort of modification of the spectrum hold true for a system of quantum mechanics, okay? Then after, more or less, I mean, there were many publications on the same period, this is why there are no dates for most of the paper here. So fermions were included, and then this setup was included in a supersymmetric setup by Alessandro Group and other people. Okay, next. Okay, so the other surprising fact, okay, so maybe, I mean, for you, I mean, for the string theory community, was not surprising, but for me at the time, that was very ignorant about string theory, was very surprising. Okay, so that this perturbation has a clear geometrical meaning. Okay, or actually more than one, they are equivalent description essentially on shell. Okay, so the first interpretation was given by John Cardy. Okay, so I summarize 5 possibility, 4 + 1 possibility here, which have geometrical interpretation. They are all related, and they are, I mean, the timing is not exactly what I'm going to, the timing, the schedule here, okay? So just to make contact with the Cardy paper, I changed the sign of the perturbing parameter here, and I write the flow equation for the action in this way. Okay, so this is essentially proportional to the determinant of the stress energy tensor. This was done by John Cardy in an arbitrary manifold, M. Okay, so it might be the cylinder or might be the circle or other setup. Okay, so this term here, this small part, first order in d tau, can be on this, since this is quadratic, we can perform an Abba-Stratonovich transformation, which is just mean a Gauss integral. And this is related to this identity. Okay, it's a bit unclear because there is a window there. Okay, but the important part, okay, on the right-hand side, you have something which contain the auxiliary variable is a sort of auxiliary metric, which is h squared, essentially, there. And there is this linear term here, which contains the stress energy tensor, again, directly coupled with to the metric H. Okay, this auxiliary, or this where you perform this functional integral. Okay, so the appearance of this term just means that if you start from flat, yeah. Yeah, just. Yeah, I guess I can try to describe. But, yeah, let's leave it. I mean, we are more or less. Okay, we can give up and carry on. Yeah, it's okay. Okay. So due to the presence of this term here, linear term in H, it means that essentially the T-bar perturbation is related to a change of metric. Okay? And the other observation that this term here, proportional, well, its coefficient here associated to H square is at the denominator. So when you send delta T, so you do small variations, small perturbation around a given point, then this integral is completely dominated by the saddle point solution. Okay, the other thing is that in principle, when you do this functional integral over H, you have to sum over all configuration, even the configuration that change the curvature, for example. But it is possible to prove, maybe calculating the Ricci curvature, that actually they do not contribute. And this is happened because you impose the conservation of the stress energy tensor. Okay? So essentially, you sum all only on diffeomorphism. Okay, so the other geometrical interpretation was given by Tolley in a beautiful paper where he made a connection between T-bar and massive gravity. So the idea is that you start from your preferred action. This is essentially the matter action as 0, and you define two set of field band, this E, which is you call auxiliary dynamical field band, which has associated metric G mu nu, and this E is coupled to a second field band, which we call F, and associated to a second metric. Okay, and then the T-bar deformation. So this second field band F will be the metric where the T-bar deformed theory lives. Okay, so the idea is the following. So you add to this matter Lagrangian or matter action, you add a gravity action, a topological gravity action, which is actually very simple, is given by this expression. Okay, so the difference between E and F appear in this expression here. And then the next step is to minimize the total action, matter plus this gravity part, and you get the T-bar deform matter action just in this way. Okay, so it's an equivalence, it's an on-shell equivalence, as most of the equivalence we will deal with. Okay. The second, a third formulation, I mean, as I say, they are essentially equivalent. So knowing enough at that time, and maybe only one of these would have been sufficient, but I think it's nice to see, to interpret it in many, from different point of view. So the other interesting, so related, is that, yeah, it's related to, from what we already noticed, to a coordinate transformation. Okay? So in particular, if you know, this is the TT bar operator, and if you know your Baire Lagrangian, your initial unperturbed Lagrangian, you can, and you know the metric, you can reconstruct the action, the perturbed action, using this identity. Okay? And actually, for the TT bar operator, the coordinate transformation, so the field band, essentially, it's related to this object, to this infinitesimal transformation, which is actually exact, so you can actually integrate globally and map a solution, your initial solution and perturbed solution of your equation of motion to the perturbed solution, okay? So this is useful, at least from my point of view, which were or for people interested in integrable models, solitary solution in Sine-Gordon or other models. So this is the equation. You need to integrate this, which is not always trivial, on shell, and then you move from the unperturbed solution to the perturbed one. Okay, so this is an example. This is the solution. This is a particular solution of the nonlinear Schrödinger equation, which is a non-relativistic model, but of course we can generalize the TT bar perturbation also in that case. And you see that this is called Peregrine solution. It's a sort of freak wave which is forming. I mean, everything is flat at certain times, and then it's forming, picking up. Okay, so this is the underformed solution, and then if you switch on tau, positive tau, this solution becomes larger and larger, bigger. It looks as it takes more space, and then if for the other sign of tau is shrinking, okay. But actually, this picture is a bit deceiving because what you have to look for is the distribution of energy. And actually, the two behaviors are exchanged. Okay, the energy is spreaded in this case, and it's less spreaded in this case. Okay, so there is a fourth description, which is probably the most interesting to this audience. But again, it's related in some way to, as actually was the first proposal, to the previous description. And there is a fifth description by Sergei, which should be here around. And it's related to this generalized uniform Lycon gauge, where you introduce a parameter, and this parameter is actually can coincide with the TT bar perturbing parameter. Okay, so as I said, for the homological reason, the TT bar perturbation is very, very spatial. And it's spatial, so we are interested in it because we have a quantum result. Okay, so it's the first model, irrelevant perturbation, which can give us exact result. But at classical level, there are many other perturbation on operator that we might study. And so it's a huge family, of course. We call them essentially stress energy deformation. They have similar feature, but not a quantum level. Okay, so one of these operator, okay, is a classical field, essentially, composite field, is what was introduced by these people, and it's called root TT bar operator, and is defined in this way, okay, but this flow equation is actually coming from result in 4 dimensions that I will briefly describe later. And what is surprising and is highly non-trivial, is actually this perturbation is commuting with the TD bar operator. Okay, and this is not trivial, and we think it's probably the unique operator at classical level which commute with the TT bar operator in this way. Okay, so at least at classical level, you can first perturb with TT bar and get, I don't know, Nambu-Goto theory, and then you perturb with this root TT bar, and you get a deform, so a double parameter deformation of free theory. Okay, so what's going on at quantum level? Okay, so again, historically, we first obtain the result at quantum level, and then we try to give a classical interpretation. So at quantum level, as I say, these are integrable. You start from an integrable model where you know the two-body amplitude. So there is a factorization property which is called Yang-Baxter equation. And then when you solve the Yang-Baxter equation together with unitarity and crossing constraint, then you are still left with an ambiguity. And this ambiguity, so is a scalar factor which satisfies all these equations trivially. Okay? This ambiguity, usually you fix it using minimality assumption. And then you can also include have new poles associated to new bound states that will change the theory, okay? Because it will change the content of the mass content of particle content of the theory. But however, you can also avoid that. So if this CDD factor is an appropriate scalar function, you can avoid the introduction of new particle. Okay, so it's really an ambiguity. And the simplest ambiguity is related to this scalar factor here, which contains a parameter tau, which is the same as the TT bar perturbing parameter. Okay, so if you, as I mentioned, so if you know the exact scattering matrix, so you can use thermodynamic Bethe ansatz or nonlinear integral equation type equation, and just in which the kernel it's related to the S matrix. Okay, so if you have your original thermodynamic Bethe ansatz equation, you just change the kernel in the same way, and you get a new equation, and and then, for example, if you do that for free bosons, like Dubowski and collaborator did, I mean, you see before 2016, you get this spectrum here. Okay, so this was for free boson, and it was generalized to an arbitrary CFT, but it's not a huge result in the sense that we knew that it was possible to do it to experience an integrable model. Okay, and then the other approach, I think one has to be more careful with this, but essentially is to start from the classical flow equation, replace a classical quantity with a quantum quantity. Essentially, at the end of the day, what you get is that the flow equation for the Hamiltonian in Euclidean signature is the same as the flow equation for the Lagrangian. You get expectation value, and you use this factorization formula of homological that can be written in this way. And you identify the various components or expectation value of the stress energy term, so in terms of the energy or the pressure, the derivative of the energy with respect to R, and the momentum, which is conserved because we are perturbing the theory with a scalar operator. Okay, so this is what you get at the end. So the classical evolution equation for the Hamiltonian density is becoming this evolution equation for the spectrum, which is a well-known equation. It's called the Invisit-Burger equation. And this is, actually, you probably know, it's the simplest equation where you have wave breaking or formation of branching of the energy, like in this one. So it's a very well-known equation in hydrodynamics. Okay, so in particular, when you start from a state in the zero spin or zero momentum, p equals 0, then the solution, the simple solution, the solution is very simple. It's just, again, a redefinition. So from already at this level, you see that there is a geometrical interpretation, okay? So a variation of tau is related to a variation of r on the right-hand side, okay? Okay, so this is the result. This can be also obtained in what I think is a more rigorous way using thermodynamic beta ansatz, the CCD factor, et cetera, is actually directly related to the approach proposed by Sergei. Okay, so this is essentially the finite size spectrum of a general integrable model theory. So there is crossing. This is related to integrability. Actually, this is the Ising model, so it's trivially integrable. So the question is, what happens if you perturb? So you switch on this parameter tau. So what happens is the following. So if you, for example, consider the ground state, so negative energy, everything is normalized such that at large r, the ground state goes to 0. You see that this energy level is bending on the right in this way. Okay, so it's essentially a pose singularity for the conformal field theory is bending this way as branch point is formed there. Okay, so the question is, what is the meaning of this branch? And we think is non-physical, so it's related to non-physical boundary condition. Okay, for the other levels, or for example, the positive one in the conformal limit, they are bending in the other way. Okay, toward negative r. Okay, if you change the sign of tau, then these two situations they swap, okay? So we have one situation, which is usually called good sign, where this phase transition happen for the ground state, okay? And then there is a bad sign where excited state disappears, okay? They become complex, and that's the situation where we call a bad sign. Okay, so it's a sort of, so if you decide to get rid of this state that become complex, it's a sort of something like a finite number of the system with a finite number of degree of freedom. Okay, so is this okay? So this is picture that we can get rid of the excited state or that become complex, then there is strong support for it. So we saw the picture where this solution is become wider or narrower, and this is the proper picture I took from a nice paper by Cardi et Doyon. But actually, if we go back to the quantum version of the nonlinear Schrödinger equation, which is called the Lieb-Lineger model, it's amazing that a TT-bar-like perturbation start from, this is a standard delta function interaction. It's a boson gas, hard boson gas in 1 plus well, in non-relativistic theory, in one space dimension. Okay, and you see that including this perturbation, then the particle become of finite size. Okay, so this is called hard rod gas, and it was already known in the literature before we were talking about the TT-bar or TT-bar-like perturbation. Okay, so it means that if you put your system in a finite box, okay, then as you switch on in one direction the TT-bar perturbation, then you cannot accommodate more than a certain number of particles in your box. Okay, And this is why you have less excited state, and you have a finite number of excited state of your system. I think this is the previous one. I think it's a very nice picture. But we have connection, so immediately connection with ADS CFT were put forward at that time. So the idea is that what happened in the bulk of ADS when you switch on the TT bar perturbation on the boundary. So, and the net result by Metzey, Verlinden, and another is that it's a bit like, so if you look for the excited state, this is actually the wrong sign for the TT bar perturbation. It's like putting putting a BTZ black hole in a box, okay? So it's like putting a cutoff. And then as the distance between cutoff and the horizon depend on this parameter tau, as you increase tau, the cutoff is approaching the horizon of the black hole. And at a certain point, if the black hole is very energetic, then it will be, it will not fit in this box. So it should go away from your spectrum. A third way of seeing that the disappearing of this of the energy levels which become singular is related to a nice paper by Domenico and collaborator. So they are studying now Yang-Mills theory at a quantum level, and they managed to essentially reconstruct the full partition function, okay? Using instanton-like subtraction, and this is the result they got. Okay, so for tau greater than 0, there are certain let's say energy level which have a pole singularity, and after the pole singularity they should get out, go out, move out of the partition function. Again, it's signally a sort of finite number of degree of freedom, and in the other direction, in tau, for tau smaller than 0, they also manage to do the right, to find the right subtraction to make the partition function finite, okay? And this is the phase diagram discovered by Domenico and collaborator. Okay, it's much richer. This is the undeformed Yang-Mills, and there is an extra phase, which is this mixed phase where non-perturbative contribution due to the presence of TT bar operator emerge. Okay, so next I will move to higher dimension, okay? So the sad thing about higher dimension, if you are not talking about strings, is that essentially we lose quantum information in the sense that we don't know how to quantize the system, and that's obvious, of course. So in higher dimension, essentially we talk about generic stress energy deformation, okay? So one important thing we understood, so one important lesson is that, okay, so the people is always asking, oh, what can you learn more? What did you learn more using this TT bar? Yeah, so the main lesson that we have a flow equation for the Hamiltonian, a flow equation for the Lagrangian. And using this flow equation, you can actually prove that all this stress energy tensor deformation are actually metric deformation, okay? So they are on-shell equivalent to a theory which are different with a different metric. And then you can couple TT bar with Einstein gravity. You can find connection with massive gravity. And then there are connections with nonlinear electrodynamics, and in particular with the so-called modified Maxwell theory recently introduced. okay? So here there is the Bohr-Infeld action, which is the simplest theory. It's a very well-known theory of nonlinear electrodynamics. It was introduced before renormalization of quantum field theory was introduced, okay? So one other surprising fact, maybe a posteriori, I mean, discussing this here, it doesn't look so surprising, is that also the Bohr-Infeld action, okay? So which, sorry about that, satisfy a flow equation in the parameter tau, which is the inverse of the tension of the brane T, okay? And more recently, in 2020, it was introduced a variant of the Maxwell theory, which was called ModMax, okay? And this modification of Maxwell theory is somehow unique, is the unique nonlinear duality invariant conformal extension of Maxwell theory. Okay, this conformal extension, it means that it is associated to a perturbing operator, which is classical, which is marginal at classical level. Okay, so we don't know how to quantize either one or the other of this theory, of course, so, but we are playing with classical quantity. And the other amazing thing is that this ModMax theory also satisfies a flow equation. The perturbing operator is this, was named by Alessandro and collaborator root TT bar flow, and it has this form here. And is again, even at this level in four dimension, is commuting with the TT bar perturbation. Okay, as we think is the only commuting operator with the T bar-like perturbation. So with this perturbation here. Okay. Okay, the last thing is we can, okay, so I think we have no many restriction apart from causality or physical stability or other restriction that, you know, for every perturbation we should investigate, or superluminosity, etc. etc., etc. So the simplest example, that is the simplest generalization to TT bar in higher dimension, it's a perturbation which is quadratic in the stress energy tensor. For these cases, but actually this is very general, you can move from this description here for the Lagrangian to a description in which the metric is flowing. Okay, the original model on a different metric, dependent, it's a dynamical metric which depend on the stress energy tensor. And actually, so this is a very nice equation, and actually this can be exactly solved, at least in this case, for the quadratic perturbation using the method of the characteristic. It's an exponential with some slightly complicated exponent, but what is important to finish our discussion, and then you can also solve this, for example, in a perturbative way. Okay? You need to know the variation of tau with respect of T, the stress energy tensor with respect to tau, but then you end up with a closed system that you can solve recursively, and it's really a program which takes 2 lines to get coefficient up to 200 or okay, so what is important that what I wanted to mention, that you can do this expansion. Okay, so first order, you have this expansion, and then correction that in general are an infinite number of correction. What's happened and what is expected is that if you set d equal 2, you go in one case to the TT bar perturbation, and the series truncate a second order, so the metric is quadratic, and this is essentially the result we had at the beginning. But the other interesting model is when you go to D equal 4 and you demand that the stress energy tensor has only two independent eigenvalue with multiplicity 2, then surprising the series, they're truncate at first order. Okay? So, and this is also, if you look at the Bohr-Infeld equation, actually, if you look at the whole paper or all the review, then there is this metric appearing there. This first order perturbation in this parameter appearing in Bohr-Infeld. Okay, so once you have the metric, then you suppose you know the unperturbed matter action. You add simply in this way the unperturbed operator, and you dress it with the new metric, and then you get the deform action. Okay, so a sort of gravitational dressing. Okay, this was my last slide. Thank you.
Hello. Yeah. So these fractions that appeared in the hypergeometric function, do they mean anything, or are they just?
Well, the meaning, I don't know, but I think it's the same generalized hypergeometric function you get also in R dimension when you study this nonlinear hydrodynamics, electrodynamics model. The self-dual, the paper by Aschieri and
So in this context, there's no specific physical.
No, there is no specific reason to have that number. Yeah.
Thank you.
So the question, I guess, is can you generalize this, and can you find other generalized hypergeometric function? And we don't know. Yeah, probably yes, but.
I have a simple question. Is there anything known? Is it working? Is there anything known about 2- and 3-point correlation functions of stress energy tensor of a TT bar deformed CFT?
Okay, so it's a tricky question, I think. Yeah, no, from a certain point of view, I think there are papers by Cardi and many other people which tackle the question of correlation function. It's a tricky question because in some case, in the real space, coordinate space is not easy to get because you have, so for example, if you use this change of coordinate, the change of coordinate, it's state dependent, so it's unclear exactly what you have to do. The other question is that the theory is somehow non-local, at least in one direction of tau, so it's unclear exactly whether this correlation function. Okay, if you put cutoff and something like that, then there are the description of the correlation function, which looks consistent. But I didn't, work on that, so I'm not sure. There are also other results by Elijah and Stefano on form factor for TD bar perturbation, and also in that case, they seems to work. But it's hard to, you need to compare with something to tell that that's exactly the answer, the correct answer. And I think higher than a 2-point function, I don't know, yeah.
I'm not talking about arbitrary operators, it's just stress energy tensor, the object you are dealing with, right?
Okay, so correlation function between the stress energy tensor.
Just say 2-point correlation function.
Yeah, I don't know.
You don't know.
The Nambu-Goto action that you get is in 2 dimensions.
Yes, it's in 2 dimensions. You can get, with this generalized stress energy
I mean, you talked about the Nambu-Goto action that you
Yes.
got, but in 2 dimensions.
That's in 2 dimension, but we can, in higher dimension, if you introduce the appropriate stress energy tensor deformation, you can go to Nambu-Goto in higher dimension.
Okay.
And for higher dimension, mean in space x to the d or whatever, yes.
You mean 4 or you will go to 26?
So in 4 dimension, yeah, for
to
example, in 4
26.
dimension, you can get it.
Not 26.
Well, 26, no, well, 26, you can get, okay, so depend on what you think about the target space or not. In the target space, you can add as many bosons you want, and you go on to 26 without problem. So from the string point of view, there is no problem. Okay, it's when you want some sort of Nambu-Goto in a higher dimension, space-time dimension.
So thanks for the talk. So you mentioned this nice progress on the Young-Mills on the sphere for the partition function. So I was not aware of that. So was there some nice progress on how to define the quantum operator in curved background?
Okay, yeah, there is some paper about that.